Good afternoon, my student. This is your Professor Nurani. I am welcoming to your fall semester. I have had a first class with you last week. Today we are going to start the actual experiment for this laboratory class. Today we are going to talk about experiment number 1. So in this experiment, the title is Dimensional Accuracy of Rapid Prototype Samples. I shall give you the actual title in the handout, but this is basically the summary of the title. Now, in all the experiment, I always try to find out what we are doing, why we are doing the experiment, how we are going to do the experiment, and what is the expectation or result. And if you can answer these 4 questions in all the reports you will submit, you have accomplished the goal of my class. And that is what I am going to emphasize. As I said, I'll give you a lot of handouts before you come to the class. We are developing this short video to give you an overview of what you are expecting to do in this experiment 1. So as I said, what we are doing, our main goal is to calculate the X and Y shrinkage or expansion factors of the rapid prototyping machine we are going to use here. We are going to use the Stratasys, one of the top rapid prototyping manufacturing companies of the world, and we have a couple of their machines. One of the most famous one is the FDM 270. It's a fused demonstration modeling. We are going to use ABS or PLA materials, and we are going to find out the X and Y shrinkage or expansion factors of the samples that come out of this machine. So you might ask why we are doing that. We bought a new machine from Stratasys. Now we are going to find out these shrinkage or expansion factors. What happens when the machine is sent to the laboratory, it comes with a default setting. But things might change. So we need to, every purchaser need to go through this like a calibration process to find out the default setting and change the default setting so that when you make something, it turns out to be good with a good accuracy. Another reason why we are doing this thing, let me tell you, this rapid prototyping technology was launched in 1989. That's the year I came to Loyola Marymount University as the associate professor. And since then, this industry has gone through tremendous revolution. But when the industry started in 1989, it has several problems. Although it was rapid prototyping, the speed was not very high. The speed was not rapid. Also, the types of materials that were available were very limited. And the number 3 problem we had is the accuracy. You make something in rapid prototyping, however, the dimension that come out is not the one you designed in SolidWorks. So the accuracy has still been a problem with the rapid prototyping industry. The first 2 problems have been addressed already with the advancement of new microprocessor technology. The speed has become much faster. Also, the researchers of the world have done a lot of research and come up with a lot of new varieties of materials. Accuracy is still not good for all machines. And it's one of the concerns of the people of Japan, especially because they are obsessed with precision. So today my goal is to address the accuracy problem. And by doing a simple experiment, you will be able to understand the gravity of this situation. So that is why we are doing this experiment. How we are going to do the experiment? We are going to develop a Christmas tree, as you see over here. It has the length of it has 5 branches. The bottom branch is 125 millimeter long, 25 millimeter wide, and the next one 100 millimeter, 75, 50. This is a Christmas tree that was designed by NASU, North American Steel Lithography Society group, and they sent us this Christmas tree STL file to all purchasers of rapid prototyping machine. So I have got that STL file and I have used that file to make a Christmas tree. I also want you to design this Christmas tree based on these dimensions although these dimensions are there, we are basically trying to measure the x and y length of each section. We are not going to measure the z direction. So I like you to keep the thickness like a 0.2 1/4 of an inch. You have to convert it to millimeter so that we don't spend a lot of materials to make the Christmas tree. So we are going to make this Christmas tree using our FDM 270 machines. Once we make the Christmas tree, we are going to bring it back to the classroom, and we are going to measure the dimensions 5 times, each dimension 5 times. If you come to this sheet, you see we are going to make 2 Christmas trees, A and B, and they look similar, but we are going to make them at 90 degrees to each other, and we are going to make measurements of both A and B. So for A, if you take the measurements of 125 section length, we are going to do it 5 times. And then we are going to take the section 100 millimeter 5 times, 75, 50, 25. Then we are going to B, because we are putting at 90 degrees to each other, we will start with the 5 and then 10, 15, 20, 25 millimeter. And correspondingly, we are going to have 5 measurements. So we have 5 measurements of each section. Then we take the average. We already know the nominal size, like 125. We are going to find a mean error, which is average minus nominal. Now, based on all these calculations, we are going to plot them on a mean error versus dimension. You are basically going to use an Excel sheet. Your Excel is very powerful. So when you plot this mean error versus the dimensions for Christmas tree A, the slope will look like that. And from the slope, your Excel sheet will already give you a slope. And so our goal is to find this slope for both x and y directions. We are not measuring any dimensional error in the z direction, because the accuracy in z direction is pretty good for rapid prototyping. So once we have found the slope, then we are going to calculate the new shrinkage factor. Remember, this machine is sent to us with a default setting. The manufacturer already know that things shrink in real life or expands in real life. So they have put a factor. In the old days, the things used to shrink most of the time. So the main emphasis was on the shrinkage. So how do you find the new shrinkage factor? We are going to use a default setting that we got from Stratasys many years ago. It is 1.007. And so to find the x and y shrinkage factor, we are going to use for the x shrinkage factor, it's the default setting plus minus the slope. It's the new slope that you have got from the Excel sheet. The default setting, is equal to 1.007. So you use that default setting and add or subtract the slope to find the shrinkage factor, or in some case, the parts expand. So if it expands, we need to bring it down. So as I said, for the expansion compensation factor, use the same formula, but basically you have to subtract the slope. Another thing you have to remember, the new shrinkage or expansion factor cannot be less than 1. That's the direction that came from manufacturing industry. So the idea of this experiment is that if we find the new shrinkage factor, we go back to the machine and change the default setting with the new factor. That way the part that is made with the new shrinkage factor will be more accurate than without putting the new shrinkage factor. So we are addressing one of the 3 problems of rapid prototyping industry, the accuracy problem. Because why this accuracy? Why we are talking about this accuracy? Because remember, in fuse deposition modeling, the materials start as solid. It undergoes through a tremendous heating process and it becomes liquid. And then when the liquid drops on demand on the substrate, it becomes solid again. So the materials undergo change of phase. So by undergoing change of phase, it has a tendency to shrink or expand. That is the main reason why you're doing this experiment. In your theory, you need to explain how the fuse deposition modeling works, and the main purpose of this shrinkage or expansion is the materials undergo change of phase. So in this experiment, you will be learning rapid prototyping technique. You will be learning one of the problems of rapid prototyping technique, which is the accuracy. And by doing a simple experiment, we are going to learn to recalibrate the machine that will keep producing a lot of accurate materials for a long time. Anytime you change the materials or you change the FDM head, you are required to undergo, make this new calculation so that the parts that you make after that, it becomes accurate. So I'll give you more information about the experiment in person, but this is basically the summary of experiment number 1. Thank you again. We'll see you again for the second experiment.